So because so many people are out and we're trying to do history of atomic structure, we're going to do it this way. You have all of the notes in your yellow books. They are things that are underlined and highlighted in grey. They are things you need to know and that you need to be able to replicate on a paper. It's not a lot of understanding, but this is where we are at. You will by now have played with this link. It shows you some of the people involved in the development of atomic structure, and hopefully you've been able to figure out what Rutherford's atom actually looked like to get the results that he did. So to start with, we go to pre-Christ and the Greeks, and we imagine Democritus in his toga with the lads drinking wine and grapes and talking about what makes up everything. And he came up with the idea of everything was made of particles, and he called them atomos, now with a Z, not an S. So if we were drawing his particle in 2 dimensions, his atom, it looks like a circle or a sphere in 3D. We have to wait 2,000 years later to get to John Dalton, and he again was thinking about things, and he came up with his own atomic theory. He uses very specific language, and you need to be able to replicate that language. So the first thing that he came up with is that matter is made up of small indivisible particles, and again called them atoms from the Greeks. And he also decided that all atoms of the same element will have the same mass and the same chemical properties. And you can see over here on the right, his atom drawing is no different to what the Greeks were. Hopefully at this point, the fact that he thought all atoms have the same mass is making little light bulbs go out in your head, because we now know that that is not true. And the reason why that is not true is because we know the existence of isotopes. So that is a limitation of John Dalton's atomic theory. John Dalton is also the gentleman that came up with the law of conservation of mass that says matter is neither created or destroyed in a chemical reaction. And when we get to form 4, 5 and we start doing maths, you will see that if I have 10 grams of reactants on my left, I will have the same number of grams on my right, no matter what form it's going to be in. So we then move on to a gentleman called William Crookes, and he worked out that these things called cathode rays are made of tiny particles. Now he did this using a thing called a vacuum tube. He put a Maltese Cross, which I'll show you in a second, and he looked at the shadow. So this is the diagram of it. You won't ever have to reproduce it, but essentially what he is saying is that there are, I'll go with yellow, there are tiny particles coming out from this cathode, and the Maltese Cross blocks some of them, which is why we get a shadow, and the rest of them are able to go straight through and hit the back of the cathode ray tube. Okay, so let's just see what this looks like in real life.
This is a simple demonstration of a cathode ray tube in which we use a Maltese Cross made out of aluminium as the anode, and it casts the shadow of the electron beam on the front of the glass tube. Now, with 5,000 volts across the cathode and anode, electrons come off the cathode, they move towards the anode but cast a shadow on the glass tube at the front, and it's the tube is lighting up under the influence of the electrons striking it. Now I can flip the anode out of the way, and what happens is we're left with a positive image on the front of the tube rather than the negative image that you can see at the moment. And here we go, we flip it down and you can see a positive image there.
Okay, so what's really, really important for this is that you need to know what the observation is. If you put something between the anode or something between the cathode and the back of the tube, there's something is going to happen. So it's either going to leave a shadow, or in this one. So this is a little paddle wheel. The gentleman will explain it. It is on little, not quite levers, but it's on a support, and it's what will happen now if my cathode is over on this side. What is going to happen to my
This is a simple demonstration of a cathode ray paddle wheel. Now in this you can see the cathode is on the right and the beam of electrons goes across to the left. There's a little paddle wheel there that lights up when the electron beam hits it. Now you can see the electrons are transferring their momentum to the paddle wheel, and it moves along towards the left, and then it stops because it's kept there by more electrons. And here's one in the darkness, and you can see it really light up. The paddle wheel's coated with a luminescent material that lights up with the electrons.
Okay, so again, you need to know the observation. If there's a paddle wheel, it's going to move away from your cathode. So you need to make sure you are aware of that. If you ever get to see the Science Museum in South Kensington in London, this is J.J. Thompson's original cathode ray tube that he did a number of experiments. So he has a number of claim to fames. So before we get into what his claim to fames are, this is his experiments.
Okay, this is a cathode ray tube. What it essentially is, it's a vacuum chamber. There are no gases inside this glass tube. The only thing we have are two electrodes, one's called the cathode, the other's called the anode, and a fluorescent screen in the background. It's coated with some type of fluorescent material. When I turn the power supply on, we'll see a beam that causes that fluorescent screen to glow. Looks like a nice straight line, doesn't it? We call that a cathode ray because it emanates or begins at the cathode and shoots across over to the anode. J.J. Thompson was working with cathode rays. We really didn't understand what they were. I mean, we have electricity going in one side and coming out the other, but there's nothing inside to conduct it. It's a vacuum tube. So he decided to apply a magnetic field to this cathode ray, and he found something interesting. We apply one pole of the magnet to this beam and we'll see what it does, and then we'll flip it around and see what the other pole does. This is my favorite part. Can you see what's happening to that beam? What does it appear as though it's happening to it?
It's moving.
It's moving, it's being repelled, isn't it, by the magnet. When we flip the magnet around, and what do you think is going to happen this time? Well, if it's being attracted on one pole, see how it's being attracted there? Let me rotate it so the kids on this side of the room can see it. See how it's being attracted there? And then the other pole, do you see how it's being pushed down? What does that tell me about that beam? It has a what? It has a charge. Let me tell you about the poles of the magnet. The one that pushes it away is the negative pole. So what does that tell you about the charge of those particles? Negatively charged particles. And J.J. Thompson was actually able to do a charge to mass ratio of these particles, and he found that these particles were about 2,000 times lighter than a hydrogen atom. Now, at the time, that was very profound. What did Dalton say? Are there any particles smaller than an atom? J.J. Thompson just found something 2,000 times smaller than a hydrogen atom. Why is the hydrogen atom and something 2,000 times smaller than it so profound?
Hydrogen.
Because hydrogen's the smallest atom, isn't it? So if we found something 2,000 times smaller, we have found our first subatomic particle. And it's called the electron. Okay, that'll work good.
Alrighty, so this is J.J. Thompson. He has a lot of claim to fames. So the first thing he did was he worked out that the cathode ray particles that Crookes found, they are now negatively charged. Okay, we know them to be electrons. He knows that they travel in straight lines because we get the shadows or we get the paddle wheel moving, and he found out that they are deflected by an electric or magnetic field. So these ones are their properties, and you need to be able to write them. Okay. The next thing that he did was, so that's his first claim to fame. There's an Irish link to all of this, and these negatively charged particles are named electrons. A gentleman by the name of George Stoney out of NUIG, as it is now. So that is the Irish claim to fame. So it's the electrons are these negatively charged particles. And Thompson also measured the charge-mass ratio of an electron. So he worked out that an electron has its mass of 1890, which is teeny tiny, but not so teeny tiny that it won't make paddle wheel move or create a shadow. So even though the mass we would consider to be very small, it is not. And this is Thompson's second claim to fame. His third claim to fame is coming up with his atomic theory. And his atomic theory, it's called the plum pudding model. And you have to be able to describe it. This is how we draw it. And if you were labeling it, we would say it is a sphere of positive charge. So this is our sphere. And it has negative electrons embedded in it. And it's really important that you use the word electrons. If I had €1 for every time I've said it and it doesn't happen, I'd be rich, because Thompson knew about electrons now. So they're not just negative particles, they are electrons. And this is now where we have our model. So as we said, that's his third claim to fame. So Thompson to me is a real important one. We then have this gentleman, Robert Millikan, and he did what's called an oil drop experiment.
Voltages increase further. Some drops will be. In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thompson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
Okay, so good news for this. Why are you not now
Yes.
going forward? I don't know why you won't go forward for me. Here we go. So this is Robert Millikan. His claim to fame is he determined the size of the charge on the electron. You don't have to do any of the weird and wonderful maths that go with it. You can literally just give them this. Okay, everybody forgets Millikan. I presume his mom doesn't. Look how smart he is. Okay, so he determined the size of the charge of an electron. This is just telling you how he did it. He used X-rays to ionize the air. These oil droplets were covered in electrons. He adjusted the charge until the drop hovered, and then he used that in his maths. Now this used to play, but it's not showing me the play button. It's the exact same as the previous video. So Robert Millikan determined the size of the charge on an electron. This last gentleman, his name is Ernest Rutherford. He was a Kiwi. He worked out of Cambridge University, and he was ridiculously arrogant, as lots and lots of quotes from him. There's only physics, the rest is stamp collecting. Okay, so while he was arrogant, he was also a really good scientist. This you've seen when we did the link with the atomic theory. I'm going to move on to this because you don't need it. So this is Rutherford. He's not going to play now, is he, today? No, he is not. No, he is not. Okay, so you're going to have to get me explaining you what's going to happen. So this is Rutherford. He took an alpha particle emitter. So alpha particles are just positive helium nuclei. So it's a helium without the electrons attached to it. So He2 plus. You do need to know what an alpha particle is. He fired it at gold foil, and he fully expected, if J.J. Thompson's atomic theory held, that they would all go straight through. So you can see that there's some go straight through. They were, and the language we use for this, that there are some that were deflected, and there are a few that are reflected right back. Now, to him, this was ridiculously shocking. It made no sense at all. So he fired his alpha particles, thought that they should pass through if Thompson's thing was right, but it doesn't. So you need to know what his observations were. So he has 3 observations. Firstly, most pass straight through, some deflected, few bounce back, or few reflected. I really, really, really want to see these words. So most pass straight through, some deflected, few bounced back or were reflected. He then used those observations to come up with the conclusion. So the fact that most went through tells us that an atom is mostly empty space. The fact that some were deflected. So he worked out from that. The alpha particles are positive, and if you put a positive and a positive next to each other, they will try to get as far away from each other as they possibly can. So they will repel. So he worked out that the fact that these alpha particles deflected, they must have come close to a hard, dense core of positive matter. We now know this to be the nucleus. Okay, and again, the language in the conclusion is really important. The few that came reflected back told him that these alpha particles had to hit something head on to say that they came right back. And he decided then that it was a small, really dense mass. And again, he's calling this now a nucleus because he's figured out what it is. Okay, this diagram is going to go into your book just under Rutherford's. He made a comment about the few particles that reflected back. He said it was like firing a cannonball at a piece of tissue paper and having them come right back. It was really, really, really unexpected. So his gold foil experiment discovered the nucleus. That is his big claim to fame. Okay, and again, this diagram goes into your notes with your arrows, so you can have more than one arrow going straight through, just to prove that most go straight through, some reflected, and few go backwards. Okay, fewer reflected. These are all need to know. You throw away marks by not giving me the right language. Rutherford didn't stop there though. He also is responsible for discovering protons by bombarding different elements, again with alpha particles. Remember now, don't confuse him or forget about Moseley. I'm sorry, now I have to use my mouse to do this. So Moseley was responsible for counting protons, but Rutherford is responsible for discovering them. Now, Rutherford had loads of different people working for him. One of them is this gentleman. His name is James Chadwick, and he is responsible for doing neutrons, and he did that by bombarding beryllium with alpha particles. Okay, so in a very similar experiment, he worked out neutrons. So, your brain, this may be you, but we have to persevere. So at this point now, we have done 3 claims to fame, 1 claim to fame, 1 claim to fame that only his mother remembers. Started it all off in terms of working out what was in an atom, decided that things were atoms to begin with. He is our Irish claim to fame. John Dalton, or J.J. Thompson, so good he gets 2 pictures. This is the first proper atomic theory we had, and this is joy that is Rutherford. We still now have these little guys left to do down here, but for the most part, we are done. So I'm going to leave you with this. Find it here.
Dalton. Dalton, Thompson, Rutherford, and Bohr, Schrodinger and Heisenberg, and many, many more used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place. Dalton did experiments and said, I think it's clear atoms are tiny indestructible spheres. Thompson worked with cathode rays, said I disagree. A plum pudding model makes much more sense to me. A new chapter in atomic theory started to unfold when Rutherford played around with atoms made of gold. When a few of his alpha particles came bouncing back, he hypothesized the nucleus had knocked them off the track. Dalton, Thompson, Rutherford, and Bohr, Schrodinger and Heisenberg, and many, many more used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place. Bohr saw spectral lines for hydrogen and said, it seems to me electrons move in orbits with specific energies. Heisenberg said, forget it, there's no way to know the orbit or a path where the electron's gonna go. Schrodinger used lots and lots of fancy mathematics, made a model of the atom based on quantum mechanics. It has orbitals, and those are based on probability. The atom is a fuzzy blob of pure uncertainty. Dalton, Thompson, Rutherford, and Bohr, Schrodinger and Heisenberg, and many, many more used their brains to venture in the realm of inner space and found the world of the atom was a weird and wondrous place. Dalton, Thompson, Rutherford, and Bohr.